Okay. My name's Eden Thomas. I'm going to be okay. Well, I'm presenting Tensar geogrid applications with an emphasis on subgrade stabilization, pavement optimization, and expansive soils. I'm going to give a brief history and general overview of geogrids and then get into these applications. So Tensar is the largest geogrid producer. We're a full service provider, industry leader in soil stabilization. We have over 130 licensed engineers, and we do everything from design support from conceptual phase to follow-up during the construction phase. So a little history of geogrids. They started out as a use for alternate plastics. We started out with onion bags, as you can see in this slide, and then they started conferring with civil engineering departments looking for uses, and they started creating these punched and drawn geogrids. They're manufactured out of our facility outside Atlanta, Georgia, and these BX grids have been in use since the early 80s. Since the mid-2000s, we've switched to our next generation triaxial grids, and there's some standard applications that you may have heard of. So here's our three general grids: triaxial. They're shaped like triangles. Several triangles together have an almost circular shape. The original biaxial and the uniaxial grids. So the uniaxial grids are more for slope stabilization and mechanically stabilized walls. The biaxial grids are for subgrade stabilization and pavements, and the triax also for subgrade stabilization and pavement optimization. Oops. Oh, excuse me. What happened there? Okay. This is our filter grid product, which combines a geogrid with a filter. Comes in 3 standard sizes, depending on the size of the aggregate that you're using. So what is the function of a geogrid? Stabilization, filtration, and reinforcement. So road subgrade stabilization is the most important part of our business. We do a lot of heavy haul roads and stabilize subgrades for problem roadways. Lots of grids are being used by departments of transportation and maintenance operations, especially at MDOT. I know their maintenance yards are stocked with grids, and they're using them in conjunction with removal replacement for their expansive soil issues and for various maintenance issues that they're having. The second main application is pavement optimization. The geogrids can be used to value engineer almost any pavement section. So there you have your pavement optimization. You can value engineer almost any section by reducing the amount of aggregate or leaving the section as designed and increasing the lifespan and durability of the section. Other applications include embankment stabilization, retaining walls, reinforced slopes, also railways and crane pads, and pretty much anywhere where there's soft soils. So roads wear out from the top down, but they fall apart from the bottom up. I love this quote because roadways, a large part of roadway design is simply protecting the subgrade. And that's one of the primary functions of a geogrid. So how do geogrids work? People see this and think it's just a piece of plastic, and that's true, but there's a lot of design behind the plastic. And the first thing I would say is it's not just the geogrid alone, it's also the aggregate. So the way the aggregate functions with the geogrid along with the subgrade is going to be different in every case. So we refer to the system as a whole as a mechanically stabilized layer. So you're going to hear me talk about a mechanically stabilized layer. And as I discussed, the aggregate, in our area could be anything from your TxDOT specified aggregate to 610 stone in Louisiana to more types of flex base with a lot of fine particles in it and whatnot. As I said, our geogrids are typically 3 standard aperture sizes, and the aperture size you pick is usually going to be based on the gradation of your aggregate, because you want to make sure there's a certain amount of strike through. So we have some criteria there for the D50 of the aggregate. So there's 3 fundamental reinforcement mechanisms. And this has been studied by the federal government, especially in the 90s, by the US Army Corps of Engineers, the Federal Highway Administration, and others. And the 3 mechanisms are the tension membrane effect, and what they call improved bearing capacity, also known as the snowshoe effect, and lateral restraint. So with the tension membrane effect, I'll discuss each of these individually, give you a bit of the theoretical background. With the tension membrane effect, you're essentially adding a tensile force into the pavement section. Now, this is based on geotextiles, which were used before geogrids. So the issue with this that I think is important is a lot of people specify geogrids based on their tensile strength, but you have to know that in most sections, by the time you're mobilizing the tensile strength, you've got such a deep rut on top that the roadway's already failed in other ways. So typically we don't specify based on tensile strength. And yes, the tensile element will help in certain ways, but it's not the primary mechanism. Here you can get a little view of this in this slide. You can see there's a deformation of the subgrade to actually put the geosynthetic, whether it's a grid or a geotextile, to put it into tension to where it's actually mobilizing that tensile force. So the next is what people refer to as added bearing capacity, which is not really an added bearing capacity, but it's more of a snowshoe effect. And this means that the grid is sort of spreading the load. So if you have some wheel loads, like on a heavy haul road, or even if you're making a crane pad, the grid's going to help distribute that load to a softer subgrade. So there's that point illustrated just in a diagram. You can see how it works and how it's going to protect the subgrade in a pavement application or a soft site application. So this is the main thing. Confinement, that's the 3rd function of a geogrid. And what this means is you're basically taking that aggregate and confining it in the apertures so that it doesn't move. Typically in most roadway sections, even if you don't construct it with an aggregate, it's going to be confined right at the time of construction because you're going to have it perfectly compacted. Now, over time, as water gets in there and as it vibrates and you get holes, that aggregate's going to loosen up, and that's where some failure is going to come into play. But the geogrid, the function of it is to confine the aggregate and prevent that lateral movement. So there's illustrated with a pavement application. You've got a load from a wheel coming down, and that geogrid is going to hold that aggregate in place. And the strike through of the aggregate through the grid is what I was talking about earlier when I was talking about the necessary gradation. So if you get one thing out of this presentation, let it be this: confinement and lateral restraint of the aggregate is the key to performance of the mechanically stabilized layer. And tensile strength does not matter so much in roadway applications. So I'm going to go a little deeper into confinement just to kind of explain kind of how it works. So here you have the grid at the bottom here, and you have really 3 zones here. So you've got the fully confined zone. The closer the aggregate is to the grid, the stiffer it's going to be. So you've got a fully confined zone, you've got a transition zone of partial confinement, and you've got an unconfined zone. So this unconfined zone, usually I want to say it's somewhere between 15 to 18 inches. It transitions. At about that point, the geogrid's having no effect. It's sort of, it can vary in each case depending on the properties of the aggregate and the type of grid being used. Some grids have a higher aperture than others. They'll have a much higher effect. But the point is, if you get into some situations where you need a really robust section, you may have to use more than one layer of grid. And here's just a little diagram just to review everything we've gone through. You see you have a textile. In order for that textile to mobilize strength, you can see it has to rut a certain distance. But then you have a stiff geogrid, which is much stiffer. It's gonna keep that, keep that stiffness with that interlocking effect. So the main function is not from the tension membrane effect, it's from confinement. Again, here just showing a geotextile. Okay, gonna run right into a little bit of subgrade stabilization. Typically, you have a couple options when you got a really weak subgrade. Maybe it's a very soft clay or totally saturated or a swamp. You can excavate and replace, remove the poor quality soil. You can use a lot more stone or a sand subbase and raise it up depending on your final grade of the site. Or you can use a type of chemical stabilization, cement stabilization or lime stabilization. Or number 4, you can do mechanical stabilization. And that means using a geogrid and some type of base material. So I'm just going to get into some job site photos so you can kind of see up front, and then we'll discuss a little bit about the design. This is a gas extraction site in Louisiana. They couldn't get their equipment out, so they called us and they're looking for a way to stabilize the site. They couldn't even get chemical stabilization equipment out there because the site had such soft subgrade issues. There's a look at it. You can see it's like most of Louisiana, just a big giant swamp. There's the barrier of the site. So we lay a first layer of geogrid just right on the ground, right on the soft ground, and then just basically dump a couple feet of sand on it. And this is a pretty common application in situations like this. Usually I'd say about 18 to 2 inches, or 18 to 2 feet rather, of sand. You have a good sub base and a nice platform to build up from. Oops, get the sand down there, and then lay down a second layer of geogrid on that base, and then put some aggregate rock on top. And then you can drive all your trucks on it, all your heavy equipment, and get your work done. Just dump it right on there. Here's another example of a job site here, a temporary access road in Texas. This was I believe a train derailment. They had to get a bunch of emergency construction equipment out there. They were trying to access the site. They had a lot of issues with just general soft grounds and heavy rutting. So I've got this photo. What I like about this is it shows you they dumped this aggregate just right down in this area, and you can see the rutting off the grid, and then on the grid you can see how it's sort of spreading that load. So this is just a diagram to kind of show some of the, before I get into the design, just kind of shows some of the comparisons of some of our grids. So this is Subgrade's got a CBR of 1.1, and for the analysis done on it, it's requiring 28 inches of aggregate rock. So we can compare that, same subgrade, you can reduce that to 11 inches with TX 160 geogrid. That's one of the stronger grids with a pretty high aperture, so it's going to have a high level of confinement. TX 140 is a little less robust than the 160. It's going to require 16 inches. BX 1100 is a biaxial geogrid. The geometry is not as good. It's an older generation grid. It's going to require 21 inches. BX 1200, 16 inches. So we can always do these sort of comparative designs. We do them quite often, especially for heavy haul roads and for crane pads and lay down yards and that type of thing. And it helps the contractor kind of price out what they want to do, and if, you know, how they can save money on rock and materials. And it's all done with the Giroux-Hahn method. And this is based on work done by Dr. Giroux and Dr. Hahn. And it's utilized to calculate the thickness of an aggregate base course for unpaved roads or paved roads. It's theoretically based and empirically verified, which means basically they had some theoretical notions of their equation, but then they did a bunch of automated plate load testing to kind of verify it, and then they developed their equation where they're always solving for the height of the section based on a couple parameters. Here's some of the graphs that they came up with, and some of the equations. I don't have to get deep into the equation, but just wanted to share that with you guys. And it basically comes down to about six variables that you have to plug in. And those are the traffic volume, the wheel loads, the tire pressure, the rut depth, the influence of the geogrid, and the subgrade strength. Now, the influence of the geogrid is going to be based on the properties of the grid itself and the interaction with the aggregate. So in order to know the influence of the geogrid, you really have to have a testing record on that particular grid. So we have that for all our grids, testing verified by the U.S. Army Corps of Engineers and over 300 plate load tests. But I guess what I'm trying to say is you have to have some empirical basis for the influence of the grid. So you plug all this in. We have a program, SpectraPave, that utilizes this method. It's got 3 modules here. This is the subgrade stabilization method, and you can basically just plug in those parameters and check different roadway sections. Here's what the input screen looks like. You can put in an axle load, tire pressure, number of passes, and then your rut depth. Usually it's going to be 1.5 or 3. Your CBR of your aggregate, your subgrade CBR, and then these are the different grids that you can input, so you can compare. Come over to the output screen, and this is your output. You get aggregate fill thickness, your unstabilized section, stabilized with TX5, TX7, TX160, TX130. So you can basically just compare all the sections. We recommend a minimum of 6 inches of aggregate. That's why these sort of bump up from 4.2 to 6. And that's just because sometimes you can have problems with constructability and using the equipment. They're liable to rip the grid. So as I said, this software is totally based on the Giroux-Hahn methodology. Here's the report it spits out. So a lot of times I'll prepare these for geotechnical engineers, or they can prepare it themselves. I encourage everybody to go on Tensar's website and download this program, SpectraPave. You can download it for free and play around with it and use it on your projects. Okay, pavement optimization. This is next to subgrade stabilization. We do a lot of pavement optimization. Basically, you can use a geogrid to reduce an existing section, as is shown on the right there. Lower your cost of construction materials, or you can leave your section the same, add a geogrid, and increase the service life of the section. So this is also in our SpectraPave software, and it's based on AASHTO 93 methodology, but modified to include the structural value of the different geogrids in the section. So here's a quick little example here. You've got this section, 4 inches of asphalt, 10 inches of aggregate base course. You got your structural layer coefficients here, your structural number. Calculate your amount of easels. Now here's a TX5 geogrid, the exact same section. Note that the structural layer coefficient goes up a little bit, and that's based on empirical testing that we've done. So overall, you get a higher structural number by adding in a geogrid. So we can structurally quantify the amount of contribution of the grid. And there you have it. You can see the increase in your easels there with the TX5 geogrid. The TX5 is pretty popular among municipalities and smaller cities. They're using it a lot on city roads to extend the life of their pavements and reduce their costs associated with maintenance. Here's a comparison. Just want to show you this, similar to the other comparison I showed. There's so many ways you can look at it. You get the program. You can play with it by reducing sections, looking at different grids, and trying to hit the sweet spot for the amount of pavement life you want versus the amount of money you want to spend. So there's just an overview of how pavement optimization works. Just so you can see, you're ending up reducing, and in a lot of cases, you can reduce the amount of aggregate while increasing the structural contribution, depending on the situation. Okay, I'm going to move into expansive soils. That covers subgrade stabilization and pavement optimization. I'm going to move into expansive soils. It's a huge problem. I know it's a huge problem in Mississippi with Yazoo clays and other clays, and everybody's got solutions for them, but it's still a problem. I got these quotes. ASC estimates 1 in 4 homes in the US have some damage due to expansive soils. I found this other number here, that the financial loss to property is greater than earthquakes, floods, hurricanes, and tornadoes, all due to expansive soils. Here's a general map of the US showing where areas where they have a lot of expansive soils. The red and the blue are sort of the worst areas. So you can see here, Texas, Louisiana, Mississippi here. These have, 50% of these areas could have expansive soils. So it's a huge problem for, not to mention your homes, your roadways, pretty much any construction. So how do expansive clays work? I'll just give you a quick overview. I'm sure geotechs and roadway designers are pretty familiar with this. So the clays are composed of certain minerals such as smectite, and there's a chemical reaction that happens when they absorb water at the levels of the particle charges. So when they absorb water and become saturated, they tend to expand and swell. And when they dry and lose water, they tend to shrink. And some of the variables that are going to affect this are the purity of the clay, the amount of expansive minerals in the soil. Some clays might have more sand or silt or be less pure. Also, the weather patterns of where they're located and the depth of the active zone, which is related to the weather patterns in the soils. So I put this here just as an example. I do a lot of work in Texas, and the active zone is pretty much the depth in the ground where the moisture can vary. So the deeper the active zone, the more you're going to have, typically, the more you're going to have a bigger shrinking or swelling, because it's just a bigger piece of soil that's moving. So in Houston, it's typically 5 to 10 feet. It could be 10 to 30 feet in San Antonio. You can also have moisture changes in the soil that are not related to those variables. If you have an underground pipe or very poor drainage or something like that, that can also increase the shrink swell problem. So with respect to larger structures, usually you have a little bit of overburden resisting the force of the shrink swell. But with pavements, you tend to have a very lightly loaded structure. So this diagram kind of shows you what's going on here. You have some rain or a moisture variation, and typically at the edges of the pavement is where you're going to have a bigger moisture change than you are at the center, because you got an impervious covering at the center. So most of the moisture is going to be coming in from the sides. So you have a tendency to have more shrinking and swelling at the edges. So that's why you see those bigger loads at the edges. So typically you can observe this in the damage on the pavements due to shrink swell is going to come in the form of longitudinal cracks at the sides of the pavements. You can see this kind of thing here. It's a typical example of the type of longitudinal cracks associated with this shrinking and swelling. Okay, so let's get into some of the ways we quantify shrink swell before we look at mitigation. So first, there's a direct test. You can do a direct swell test. This is very common in the Dallas area, not very common on the Gulf Coast. It's a pretty heavy duty test for the geotechnical world. You basically load and unload the soil with moisture and an overburden, and you get a measure of the pressure. Next is the TX124E. It's a PVR calculation method. It's used a lot in Texas. It's developed by the Texas Department of Transportation, and it's based on moisture content, Atterberg limits, depth of your active zone, and whether you're going from an extremely dry state to a wet state or an average state to a wet state. So there's some decisions you make, and I see people approach this in a lot of different ways. I can give you a very, very different answer, but every geotech tends to approach this a little differently, and it typically gives you a pretty conservative answer for the amount of inches you can expect in a shrink swell. It also, there's just some information on it. It typically assumes a 15-foot soil column, which may be too conservative. Next, you have your AASHTO method, which is pretty much based on some graphs. Looks at the PI, the plasticity indice of the soil, the thickness of the layer, and the moisture conditions. This is typically much less conservative than the TxDOT method, could be up to 50% less. So I see this sometimes as well. And then I call this the boilerplate method. This is pretty common in geotechnical reports. Basically, the engineer just sees that it's got a plasticity index and a liquid limit above a certain level, and they will write it has a low to moderate or moderate to high or very high. And then associated with that, they'll give some type of generic recommendation: remove and replace a certain depth with select fill, chemical stabilization, moisture conditioning, moisture barriers, or geosynthetics. So chemical stabilization is pretty popular. It does have some problems associated with it. Anyways, I say all that to say this: there's multiple ways to quantitatively calculate or estimate the amount of expansion to be expected, but there's usually a wide variance in the amount reported in the report. Here's a diagram of how the longitudinal cracks are going to form in the pavement. Okay, lime stabilization. So this is a pretty standard guide used in a lot of situations. Lime will lower the PI and lower the shrink swell. One of the main problems you see is that people are usually not going to go deep enough to make it really effective. We discussed the active zone. Usually they're only going to do 12 inches of lime, and that's not going to be enough. You're still going to get more swelling in the active zone. The second problem is that a lot of times the lime is going to harden and become brittle. And then you have this flexible pavement and this flexible base on top, and then a brittle layer. So when it cracks, you'll end up getting these cracks that propagate up through the lime. So I discussed this fairly recently with a friend of mine who works at MDOT, who told me that in their particular district, they've stopped mitigating with lime because of that exact problem with the cracks. And they're doing removal and replacement, and they're also using geogrids in conjunction with that. Another problem with limes is if you have sulfate-laden soils, we have that a lot in North Texas. You find if you mix lime with a soil that has a certain amount of sulfates, you're going to get an expansion of the soil that's independent of the moisture-related expansion. There's a chemical reaction between the sulfates and the lime, and it creates a real problem. So, say all that to say this. You have these cracks propagating due to shrink swelling. What can a geogrid do? The idea here is that it's going to stop the crack from propagating. Just like it's taken a load, when we have loads on top, it's going to spread that load onto a soft subgrade. If you have an environmental load coming up from the bottom, the idea is it's going to spread that out and prevent a crack from propagating. So we talked about confinement. You're confining the aggregate and really creating a stiffened layer. People model them differently, but there are a lot of studies that have been performed over the years. I'm going to give you a brief overview of a few to kind of show you where we're at. TxDOT did a study in the mid-2000s, a research project. The goal was to develop some criteria for spot-based repairs over expansive soils. These were pavements that were experiencing premature distress, including roughness, fatigue cracking, and longitudinal cracking. I'm only going to focus on the longitudinal cracking because that's what we're most concerned with here. So as part of this study, they reviewed all their internal specifications and literature. They conducted a survey of their maintenance supervisors and assistant maintenance supervisors. The research was followed by a field investigation where they visited sites where maintenance repairs had been completed to assess the performance of various repairs. As part of the field surveys, the TxDOT researchers did a field review, a visual review. They used falling weight deflectometer testing and coring of the pavements. After all this, they gathered up all their best methods and they put it together in this particular book, the selection of maintenance for repairs for expansive soils. As far as expansive soils, the main recommendation came out of the Bryan, Texas district. And the gist of the repair they came up with was recycle the existing roadbed and place a geogrid on top of the recycled roadbed material, add a thin layer of base on top. And what they found in all the research and all the field investigation was that these sites that have been repaired with this method had little longitudinal cracking or no longitudinal cracking. As far as I know, they're still using this methodology in a lot of repairs. So the main areas where TxDOT's using geogrid to mitigate for expansive soils is in their maintenance repairs, and in areas where they have heavy sulfates or areas where they can't get other equipment in. There's a typical section for their standard repairs. Okay, now this is a much more important study, much more recent, much more in depth. Dr. Jorge Zornberg out of University of Texas, Austin, has lots of published work on the topic, and he did a a full study on geosynthetics to mitigate longitudinal cracking associated with shrink swelling. There was a laboratory component to the study as well as a field investigation. This right here is the current TxDOT criteria for geogrids, and he used that as his sort of jumping off point. He looked at 5 different geogrids. They're labeled GG1, well, sorry, 4 geogrids and 1 geotextile. They're labeled GG1 through GG4 and GT1. These include Tensar biaxial geogrids and a triaxial geogrid and a couple woven geogrids and laser bonded geogrids. We can compare different things. This is concerning the laboratory portion of the test. He began by wanting to develop a parameter that would take account of the stiffness of the geogrid, because as I discussed earlier, some of the criteria people are using, such as tensile strength, doesn't really correlate to performance. So he looked at developing this parameter called KSGC, and here they are. It's basically a force over a displacement, and he looked at it with different amounts of confining pressure on top, and here they are for each of these lines is one different grid, but it's at different confining pressures. And he looked at these with different base courses. You can see this example I put here is just this one type of base course, but each one of his sections, there were two aggregates and 1 sand course. The field section of the study involved 80 test sections at 10 different project sites. Here they're all here. I'm just going to go through a few of them to give you a quick idea of some of the results. This is Site 5, State Highway 21. So this site was doing a rehabilitation. The outer lane of the test sections was stabilized with geogrid and the shoulder was extended. They made 5 test sections, you can see here, each with a different geogrid, including 3 of the sections had our triaxial geogrid and 2 sections had biaxial geogrid. Oops. Here's the standard section of what they did. Existing 12-inch base course in the outer lane was excavated and replaced with a 6-inch cement treated subbase overlain by 6 inches of flexible base material. The shoulder was extended 5 feet for lateral support. Geogrid was placed at the subbase base course interface. Let's see some results. Here's one of the sections that was stabilized with Tensar triaxial 130 geogrid. Very few longitudinal cracks. Here's the TX7 is our most robust triaxial grid, and here you can see almost no cracking. Show you how they quantified it here. So here's how they quantified it with they did field surveys where they quantified it longitudinal cracks as a percentage. So the triaxial sections performed better than both biaxial sections. The biaxial sections both had at least twice the percentage of longitudinal cracks. So the biaxial sections you can see there are the GG8 and the GG1. All the other 3 are the triaxial. You can see how low the percentage of cracking. GG10 is that TX7 very robust grid, which is just what we would expect. That would be the one with the least amount of cracking. Okay, moving right along. This is the second site, Site 8, Cabeza Road. We had 3 test sections, one with triaxial TX130, one with triaxial TX5, and a control section that was completely unstabilized. Get to the results. So the control section had 33% longitudinal cracks. TX130, which is our weakest triaxial geogrid, had 24%, and TX5 had only 3% cracks. So Here's another another reading they got on the section that was stabilized with our TX5. They also did some surveys to measure edge movements that are associated with the shrinking and swelling. And after a particularly wet period, you can see here, there is some movement here. But in spite of the movement, there was not a lot of longitudinal cracking observed. And so the theory is that the grid is helping keep that aggregate stiffened and prevent cracks from propagating up through the section. So one of the conclusions of the study, or one of the mechanism theory, what this all means is that, I just took this direct quote right from the study. It's expected that the geosynthetic layer homogenizes the non-uniform surface movements in the roadway induced by settlement and heave of the expansive clay subgrade. Redistribution of the non-uniform deformations of the roadway surface then minimizes the differential movements across the pavement and transfers the location of the maximum flexion from the paved area to the shoulder areas. Basically saying that you've got an environmental load coming from below, and your grid is helping distribute that and prevent the cracking. Here's just an overview of some of the results. I told you about this stiffness parameter, kind of shows how they were rated. And this jives, these are the highest ones were our triaxial geogrids, which would be expected. And then the lowest ones go down to some of these other off-brand and textiles and weaker grids. Qualitative field performance. Here's a conclusion from the actual products that they tested. They did note that the triangular geogrids were comparatively better than those stabilized using biaxial geogrids. And they also note the rib depths. I discussed that earlier with respect to confinement. The higher rib depths perform better, and that's obviously because they're contributing to a higher depth of confinement in the base course. So I will end it here. I like to end it with a picture of Tony Soprano making a phone call. I encourage you to call me or ask me questions for follow-up to meet all your subgrade stabilization and pavement optimization needs. And I will now open it to video chat and questions.
Thanks, Eden. If anybody has any questions for Eden, please feel free to unmute yourself to ask, or you can put them in the chat box on the right-hand side of the screen.